This video is a walkthrough of answering an exam question. The only way to learn how to answer questions is by actually answering questions. It doesn't work to just passively absorb the ideas, you have to do it yourself. So as I go through this question, I'm going to put in breaks where I say, now pause the video, and you should go and work out your own answer with pen and paper. Then you can resume and see how your answer compares to mine. You'll need the question in front of you. Click on the link underneath this video and it'll take you to the question PDF. So let's get started. I don't bother reading the detailed text of a question until I know roughly what it is I'll actually need to do. I start off by skimming through the whole thing, but just looking for keywords. I want to know what's the topic and what section of notes are likely to be relevant. Here, skimming through the question, there's a whole load of specifics about a particular model, but the generic keywords that I see are log likelihood, maximum likelihood estimator, and pseudocode for finding maximum likelihood estimators, and fitting a model. So that tells me this question is something to do with likelihood and maximum likelihood estimation, and perhaps numerical optimization. I also see the y1 ... which is the sort of notation that we used for generative models and supervised models, so those should also be in the back of my head. Next, I skim through and I look for question words. The question asks me, find an expression for log likelihood and give pseudocode. There's no point trying to understand the exact model I need until I know what it is I'll need to do with it. Finally, I think through the course. I know what it is I'm being asked to do. I know roughly the keywords, so I'll think through which sections of the notes are relevant to the material. Here, to answer a question about likelihood and especially to propose a probability model, we'll need to be familiar with the notation for random variables. The question refers to a normal distribution, and I ought to remember that from the section of notes on standard random variables. And it looks like this is a question about the likelihood of a data set. We saw some of this in the section on likelihood notation, and again in the sections on supervised and generative models. Lastly, there's a section of notes on numerical optimization. What did we learn there? We learnt how to use the SciPy routine for optimizing, and mainly we learnt how we transform parameters to make our questions easily optimizable. So these are all the things that should be floating around in my head before I actually get started. Part A, Part 1. The question asks us, find an expression for the log likelihood. Let's first just write out something generic about likelihoods. Likelihood is a function of the observed data, semicolon, the parameters. Stop now and read through the question and look at all the symbols in the question and figure out, are they about observed data or are they parameters? If they're parameters, are they known or are they unknown? The observed data, well, we've got y1 up to yn. The question also tells us about capital Y subscript I. That's the distribution, the random variable from which the observations are made. And the parameters? Well, obviously there's theta, which is an unknown parameter. The question is all about trying to estimate theta. And the other symbols that we see in the question text? There's epsilon, which is known. We're told so in the question. There's n, which is known. We're not explicitly told that n is known, but we're told that it's the length of the data set we're given, so surely it is known. And the other symbol in the question is xi, and we're given a formula for it. I'm just going through this here systematically. It's a way to make sure that I read the question text carefully. I'd set out what's the observed data, what are the parameters. That's all there is that I need to know about a probability model, and if I set it out like this, I can be sure that I'm reading the question carefully. Next, what's the question actually asking us for? It asks us to find the log likelihood of y1 up to yn as a function of theta. Let's dive right in with the step we almost always take, the log likelihood of a data set. It's the sum of the log likelihoods of the individual observations. I'm writing in assuming independence here also. In all the examples in the lectures we've done this. We've assumed independent observations. We're not explicitly told in this question that the yi are independent, but at the beginning of the course when we talked about notation, we said if we're not explicitly told that the random variables are dependent, we should just assume they're independent. So that's what I will assume. Okay, and what are the random variables here? What are the yi? It tells us in the question, tells us yi is little xi plus a normal of 0 epsilon squared noise term. The question is basically asking us to bridge these two, to go from a random variable description to a likelihood function. This is a point to pause the video and have a go at it yourself. Can you figure out the log likelihood? Press play when you're ready. First, I'm going to rewrite this random variable as a normal with mean xi and variance epsilon squared. This is using what's called linearity of the normal distribution. In other words, if you take a normal and add a constant, i.e. a non-random value, you end up with another normal. We talked about this in the video about standard random variables, and we said it's used all the way throughout machine learning. This is useful because now we have our distribution in a form where we can just look up the likelihood function and apply it. Here's the likelihood function, the probability density function for the normal distribution, as you could find it on Wikipedia. I want you to learn this formula by heart. We use it all the time in machine learning. Now, this version of the likelihood function here, this is a generic formula for a normal with mean mu and variance sigma squared. But what we actually need is normal with mean xi and variance epsilon squared, so I'd better just write out the version we want. Here, I've changed mu to xi, and I've changed sigma to epsilon. It's so easy to just blindly copy out a formula and not think about what the symbols are doing, and if we're sloppy here, we'll end up with a formula full of variables that don't belong in the question, and then we'll get very confused. I've also changed notation slightly here on the left. I'm saying what I've just written down is the likelihood function for random variable y sub I. I like to work like this. I like to stick in little reminders to myself all the way through about what each variable in each formula refers to. It's just a mental crutch, but I've found it saves me from getting confused. Okay, so now we've got the likelihood for each individual observation. Let's just stick it in to get the log likelihood of the whole data set. Again, I'm being very careful here with the notation. I want the log likelihood of y1 up to yn. I have y1 up to yn on the left-hand side of the equal sign, so I have to have y1 up to yn on the right-hand side. If I had just blindly copied my formula on the right, I'd have a plain generic point little y, which wouldn't make sense. It may seem like I'm banging on about something obvious, but I've seen this sort of mistake made very, very often, and so I really think it is worth me banging on about it. There's a really simple sanity check you should do whenever you have an equation like this. Look at every symbol on the right-hand side of an equals and check. It should be present on the left, like the yi's are, or it should be a dummy variable, like I, swallowed up by the sum, or it should be a constant, like epsilon. Any dangling variables, and our equation just doesn't work. It's just like using an undeclared variable when you're programming, except that in maths we don't have a compiler to point out the bugs to us. Anyway, back to the question, just a tiny bit more algebra to tidy things up. Okay, so this answers the question. We've found the likelihood. Well, sort of. The question asks us about the likelihood of y1 up to yn parameterized by theta, and our answer here doesn't have theta in at all, which seems a bit worrying until we realize, hold on, xi is just a function of theta. It doesn't do any harm to write it in explicitly as a function of theta. If we don't do that, we're likely to be led astray when we try and do maximum likelihood estimation for theta. Okay, so this answers this question. Next part. The question asks us, give pseudocode for finding the maximum likelihood estimator theta hat. Let's just do the obvious thing. We'll define a function. Let's say define the function log-like of theta, which returns simply that expression we just derived. And then we can use scipy.fmin to minimize the negative log likelihood function. Because scipy finds minimums and we want a maximum, we need to stick in the minus sign there. And, of course, we need to tell it some sensible initial guess. Question doesn't actually tell us what the dataset is, so we can't really make the initial guess in our answer here, so I'll just leave it in as initial guess. But then we think back, hold on, what did we learn in the section of notes about numerical optimization? The big topic there was, do we need to transform our variables? So let's think again, what's the domain that we're trying to optimize over? Reading the question, it actually tells us that theta has to be in a discrete set. Okay, so what we wrote here is rubbish. Scipy.fmin is all about optimizing a continuous value, whereas here we want to optimize a discrete value. This is a good time to stop and think. How do you find the maximum over theta? Can you give pseudocode? When you're ready, press play. It's really easy to just brute force optimize over a finite set like this. We can just do an exhaustive search. We look at every possible value for theta, and then we just pick the one that gives the highest log likelihood. My code here, by the way, is written in idiomatic Python, but for an exam answer I don't care how you write your code. All that matters is that it should be good enough for a first-year undergraduate to go away and implement what you say, a first year who doesn't know anything about data science, but who's competent at programming. If you are interested in the Python here, by the way, it uses a nifty little trick. First, I create a list of pairs of values. When I ask for the maximum of the list, Python sorts the list lexicographically. In other words, it gives me back the item with the largest initial value. So I get out a pair consisting of the largest log likelihood and its associated theta, and then I just ignore the first term in the pair, and that gives me theta hat. Okay, we've finished this question. Let's move on. Part B looks a bit intimidating. There's lots of words here, lots of rambling text about river levels and droughts and so on, and so the usual trick of look for keywords, identify the relevant section of the notes doesn't work. This question, propose a probability model, it looks completely open-ended and quite scary. Here's another tip for exam strategy. Often, the examiner has some theme or idea in mind when they set the entire question. Sometimes, later parts build on earlier parts. Sometimes there are two parts which give different views of the same idea. When you see something scary and open-ended, like propose a probability model, what it usually means is, okay, we've seen the building blocks and walked through them, now try applying it. That's one of the big themes of this data science course, applying tools to real-world data sets, and that's what this question is after. Or, in other words, part A gave us a hammer, and now we want to make all the rambling words in part B look like a nail. So, how do we start? We have to start by reading carefully what the real-world problem the question is talking about. I like to doodle as I read to help me follow. We have a data set of river levels, one record per year. For the first few years, Z1 up to Z3, the level each year was roughly what it was the previous year. Then a drought started, and every year since then, Z4 up to Z6, the level has decreased on average. So is there any way we can force this into something that looks like part A of the question? Pause the video and have a think. Any modelling question like this does take a little flash of creativity. Inventing a model, I think, is the hardest and also the most rewarding part of data science and machine learning. Here's a hint. Try thinking about the year-on-year differences. Let delta I equal Zi minus Zi minus 1. And what do you think would be a good model for these delta I? Again, pause the video and have a think. See if you can propose a probability model for the delta I's. Here's my model. The question tells us that for the first few years, the difference in levels is roughly 0, plus or minus some random variation, so I'll model delta I as a normal random variable with mean 0. And after the drought starts, it says that river levels decrease on average, so I'll model delta I as a normal with some mean minus mu. Or, writing it all in the same sort of compact notation we used in part A, we can write out the distribution of delta I like this. It depends on I through some parameter theta. I'm thinking part A gave us a hammer, and if we can just put this river level problem into the notation of part A, then we should be able to apply the answers we found without too much extra thinking. Here, theta is the year the drought started, or maybe it was theta minus 1 or theta plus 1. I always make these off by 1 errors, and the examiner won't care if you make them too. One other thing I might just write down. It's good hygiene to write out your probability models precisely, and here I'm going to assume that the delta I are independent, so that the model fits in exactly with the maths from part A, so I might as well write it down. I should mention here, by the way, that the 2021 Nobel Prize winner for physics, Klaus Hasselmann, got his Nobel Prize for developing climate models where the deltas aren't independent. His idea was that if there are correlations, if a large delta one year is likely to lead to a large delta the next year, then this can explain some of the variability we actually see in climate datasets. But for now, we're just trying to answer an exam question, not win a Nobel Prize, at least not just yet, and it's modeller's choice what probability model we propose. Our model might turn out to fit the data well, or it might turn out to fit the data badly, but it's our choice, and in an exam, we should make a choice that makes our life easy. Okay, last part of the question. Explain how to fit your model. As always, we write out a log likelihood and we maximize it. Can you write out the log likelihood? Remember, we want the log likelihood of the observed data given the unknown parameters. And the question told us we don't know any of the parameters. So we want to know the log likelihood of observing Z0 up to Zn given parameters theta, mu and epsilon. First thing I'll do is I'll rewrite it in terms of the actual random variables that we decided to use for our probability model. The likelihood of seeing river levels Z0 up to Zn is the same thing as the likelihood of seeing changes delta 1 up to delta n, where delta I is Zi minus Zi minus 1. And this is exactly the sort of log likelihood we had in part A. The only difference is that we're modelling delta I as a normal with a slightly different mean to what we used in part A, so that's what I substituted in here. And the question asks us to explain how to fit the model. Fitting the model, of course, it always means exactly the same thing. It means choose the unknown parameters to maximize the likelihood. Pause the video and have a think. How would you solve this maximization problem? Press play when you're ready. Here's how I'd start. I'd ask myself, over what domains am I searching for the maximum? Part A of the question already primed me to think carefully about this. Here, mu and epsilon are easy to optimize over for a given theta. We've seen this calculation in lectures many times already. We can just use calculus to find the maximum. And Part A taught us how to optimize over theta. So we can just put the two together. We do an exhaustive search over all possible theta, and for every theta, we can do the analytical search for the optimal mu and epsilon. Here's how we might write it down. Pause the video and read. The exam question, by the way, it asks us, explain how to fit your model, whereas in Part A it said, give pseudocode. So this question, it's actually hinting to us, you can give a high-level wordy answer and the examiner won't be too fussed about exactly how you write it down. All they want to see is that you understand the big picture. And the big picture here is, first, it's a maximum likelihood estimation problem with multiple unknowns, so we have to maximize over them jointly, even if it's only one of them that we want to know about. And secondly, searching for a maximum requires us to think about what we're maximizing over. It's not just to purely formulate just call scipy.fmin. Great, we've finished the question. I suggested earlier that you should look at an exam question as a whole and ask yourself if you can spot a theme. Some exam questions are just dull exercises, hoops that you have to jump through, but other exam questions are trying to convey a message or teach a lesson, and if you can spot the message, then it can help you see if there's anything that you might have missed. This is obviously a question about maximum likelihood estimation, but the message underneath is, when you do maximum likelihood estimation, think carefully about the maximization you're doing. First, as we know from lectures, you have to watch out for multiple unknowns. If there are multiple unknowns, as there were in Part B, then you always have to maximize over them jointly. Second, there are several ways to do the maximization. There's calculus, which we've used several times in lectures and which is perfect for simple problems. There's numerical optimization using library routines, where we need to think about parameter transforms. And then there's brute force computation, in this case exhaustive search, to find the maximum over all possible values of the theta parameter. When you're doing fancier machine learning, for example training neural networks, you'll typically have some parameters that you can find with library routines, for example the edge weights of your neural network, and you'll have other parameters like the number of layers to use in your network, and for those you have to use brute force.